A Nobel Prize-winning physicist looked at his own data he had spent 30 years collecting, and said something that stopped the entire room cold. He said, "We are not living in the universe we think we are." Not a fringe theorist, not a blogger with a telescope, a man who won the highest prize in science. And he wasn't speaking metaphorically. By the end of this video, I'm going to show you exactly what he found, why it terrified the scientific community, and what James Webb, the most powerful space telescope ever built, discovered that made everything worse. But first, quick question before we dive in. Where in the world are you watching this right now? Drop it in the comments. I genuinely want to know what corner of this strange universe you're watching from. Now, rewind. Because to understand what's broken, you first have to understand what was supposed to be unbreakable. For most of the 20th century, cosmologists had a problem they couldn't solve. Two different teams, two different methods, same universe, completely different answers about how fast it was expanding. One camp got a number, the other camp got a different number. They argued for decades. The split was so bitter, so personal, that it divided the entire field of astronomy like a fault line running through a continent. Then, in the early 2000s, something remarkable happened. The measurements converged. Better instruments, sharper data, more careful analysis. The numbers settled somewhere around 70. Everyone shook hands, the war was over. The universe, it seemed, was expanding at about 67 kilometers per second for every 3.26 million light-years you looked outward. Clean, agreed upon, done. Except, science rarely stays done. Because as instruments got even more precise, a new disagreement quietly surfaced, smaller than the old one, but far more stubborn. And this time, unlike before, neither side could find the other side's mistake. Here's how it works. There are two completely independent ways to measure how fast the universe is expanding right now. The first method is essentially archaeology. Scientists use a satellite called Planck, built by the European Space Agency, to map the oldest light in existence, light from when the universe was only 380,000 years old. A faint glow called the cosmic microwave background, the afterglow of the Big Bang itself. From that ancient map, physicists plug the numbers into the standard model, the master equation of cosmology, and run it forward 13.8 billion years. Their answer? The universe is expanding at about 67 kilometers per second per megaparsec. The second method skips the archaeology entirely. A team of scientists led by a man named Adam Rice, a Nobel Prize winner, measures the expansion directly. They use a chain of cosmic rulers, pulsating stars, then exploding stars, each one calibrated to the last, stretching outward across hundreds of millions of light years like rungs on an enormous ladder. Their answer, 73. 67 versus 73. That's not a rounding error. In a field where a 1% discrepancy makes headlines, an 8 to 9% gap between two independent methods measuring the same thing is, to use the technical term, a crisis.
The obvious assumption was that someone had made a mistake. Science always assumes the boring explanation first. The leading theory was simple enough. The stars Adam Rice was using, a type of pulsating star called Cepheid variables, live in dense, dusty regions of galaxies. When you're photographing them from billions of miles away, neighboring stars can bleed into your image. Their light stacks on top of the Cepheid light. The star appears brighter than it really is. Brighter means you calculate it's closer. Closer means you calculate the universe is expanding faster. Fix the blurring, the thinking went, and the crisis evaporates. Enter James Webb. Webb orbits the Sun 1.5 million kilometers from Earth, so far out that our planet's own heat can't interfere with its instruments. Its mirror is 6.5 meters across, coated in gold, and engineered to detect light from the first galaxies that ever existed. If any machine built by human hands could spot the blurring error in Rice's data, it was this one. The cosmology community held its collective breath. Some astronomers were already quietly preparing to move on. The tension would dissolve. The standard model would survive. Normal science would resume. Webb looked. Webb measured. Webb published. The Cepheids were not blurred. The distances were not wrong. The expansion rate stayed at 73. Rees's team published their results in the Astrophysical Journal, covering 1,000 Cepheid stars across 5 different galaxies, extending their measurements out 130 million light-years. The conclusion was unambiguous. Measurement error had been ruled out. The gap was real. And then, the telescope turned towards something else entirely and found a second problem. When astronomers pointed Webb at the deep early universe, they expected to find exactly what the Standard Model predicted: small, dim, chaotic infant galaxies still assembling themselves from raw gas, young, messy, incomplete. What they found instead were monsters. Massive, fully formed galaxies existing just 500 to 700 million years after the Big Bang. Galaxies that by all rights had no business being there. Our own Milky Way took 13 billion years to build itself to its current size. These galaxies apparently did it in under a billion. Astronomers ran the numbers. To form that much stellar mass that fast, nearly every single atom of available gas in those early galaxies would have had to convert directly into stars. In our universe, the normal rate of that conversion is around 10%. Most gas doesn't cooperate. It gets too hot, gets blown outward by radiation, drifts away. These galaxies appeared to be running at 100% efficiency, like a factory with zero waste, zero downtime, zero material lost. That's not how physics works. That had never been predicted by any model anyone had ever built. One researcher put it flatly: the initial reaction was alarm. Now, here's where it gets complicated, and stay with me because this complication matters. A graduate student named Katerina Chornok went back through the data and found something the initial analysis had missed. Many of these apparently oversized galaxies weren't actually full of more stars. They hosted massive black holes at their centers, black holes devouring surrounding gas at extraordinary rates. All that infalling material generates enormous heat. That heat radiates as light, lots of it. From billions of light years away, a galaxy with a ravenous black hole looks almost identical to a galaxy with 10 times more stars. Webb was seeing brightness. Brightness was lying. Once those galaxies, nicknamed little red dots for how they appeared in Webb's images, were removed from the sample, much of the mass problem went away. But not all of it. Even after the corrections, roughly twice as many massive early galaxies remained as the Standard Model predicts. Not enough to shatter the model, enough to crack it further. And then, in early 2025, Webb found something that didn't fit into any of these explanations.
This is the part I told you about at the beginning. Webb found a spiral galaxy. A galaxy with the same elegant, sweeping arm structure as our own Milky Way, existing within the first 2 billion years of the universe. The astronomers who discovered it nicknamed it the Big Wheel. Here's why that's disturbing. Spiral structure doesn't just appear. It requires time. It requires stability. It requires a galaxy to grow in a relatively calm, ordered way, free from the violent collisions and mergers that dominate the early universe. The early cosmos was a war zone, galaxies smashing into each other, gas clouds colliding at enormous velocities, dark matter halos still assembling themselves from scratch. In that environment, a spiral galaxy has no business existing. It's like finding a cathedral in the middle of a mudslide. But the Big Wheel wasn't alone in being anomalous. The same Webb observations that found one impossibly mature galaxy also found hundreds of chaotic, violent, clumpy systems from the same era, exactly what the Standard Model predicts. So now you have both orderly and chaotic structures coexisting in the same early epoch, when the model only really accounts for one. And then came the shapes. A study published in late 2025 involving researchers from MIT, Harvard, and institutions in Taipei found that enormous numbers of young galaxies observed by Webb are stretched, elongated, cigar-shaped, prolate structures that run along cosmic filaments like beads strung on wire. The cold dark matter model, the backbone of standard cosmology, does not predict this. It can't easily explain it. But 2 alternative models do. warm dark matter, wave dark matter, models in which the dark matter particles are lighter or behave in a fundamentally different way, allowing gas and stars to flow along the large-scale filaments of the universe in these long, stretched streams. And here is why that matters more than any single galaxy, any single measurement, any single anomaly. Cold dark matter isn't just one ingredient in our model of reality. It is the scaffolding. It determines where galaxies form, how they cluster, how the large-scale structure of the universe distributes itself across billions of light years. If the dark matter particles we've been modeling for 25 years are the wrong type, if they're lighter or behave differently or interact differently, then every prediction that depends on them shifts. The mass of galaxy clusters, the number of dwarf galaxies around large ones, the way gravity bends light across the cosmos, the rate of expansion we measure today. You cannot swap the foundation and expect the walls to hold. So here is what we actually know right now in 2025. The universe is expanding about 8 to 9% faster than our best model says it should. 2 flagship NASA telescopes confirm this independently. The discrepancy has not narrowed, it has held. The early universe produced galaxies that are bigger, more structured, and stranger than any simulation predicted. Some of the excess is explained by black holes masquerading as stars. Not all of it. The shape of those early galaxies suggests dark matter, the invisible substance making up 27% of everything that exists, may not behave the way we've assumed. And dark energy, the remaining 68% of the universe, the force driving its accelerating expansion, remains a name we gave to something we cannot identify, cannot measure directly, and cannot explain. Adam Rees said it carefully, the way physicists always do when they're saying something enormous. Quote, "The discrepancy between the observed expansion rate and the predictions of the standard model suggests that our understanding of the universe may be incomplete." That is a Nobel Prize winning physicist reading his own confirmed data, telling you plainly something is missing. Not a small something, not a correctable rounding error, something fundamental, something that has been hiding in the 14 billion years between the Big Bang and right now, in the space we've never directly observed, in the physics we haven't modeled, in the property of space-time we haven't yet imagined. Here's the thing though, cosmology has been here before. In the 1990s, measurements suggested the universe was younger than its own oldest stars. That made no sense. Stars cannot be older than the universe they live inside. The field was in genuine crisis. Then someone discovered that the expansion of the universe was accelerating, pushed apart by dark energy, and the whole picture snapped into focus. The crisis wasn't a flaw, it was an arrow. It was pointing at something enormous that nobody had seen yet. Every crisis in physics feels like an ending. They almost always turn out to be doors. Right now, a species on a small rocky planet orbiting an ordinary star in the suburbs of a mid-sized galaxy is using gold-plated mirrors and differential equations to argue about whether reality is expanding 9% faster than it should be. And they're losing sleep over it. That's not absurd. That might be the most magnificent thing our species has ever done. The universe isn't broken. Our map of it is incomplete. And the next map, whenever it arrives, is going to be stranger and more beautiful than anything we've drawn before. If this blew your mind, share it with someone who still thinks we've figured everything out. And drop a comment. What do you think is hiding in those 14 billion years? Because right now, nobody knows. And that means the answer is still out there, waiting.